Dear students, today's topic is the dispersion in non-conductors. The topic code is EMWD-S2. The electrons in a non-conductor are attached to specific molecules by binding forces whose detailed structure may be extremely complicated, especially for large molecules, and would at any point require quantum mechanics for the proper treatment. But here let us consider the electron attached to the end of a spring with a force constant K as shown in the figure. So we take the electron model in this case to resolve or to work out the relationship for the dispersion. So let's take y axis along which the E is vertically varying. Speed of the wave is v. Here in this direction may be taken z or x, whichever direction we can take, but we are concerned about the oscillation along the y axis. The electron is attached now to the, we see this is electron with a spring constant K. This is, we call there is a force, binding force we will take into account. So the K force we will take that. Now the binding force Fb is given by Fb is equal to minus Ky, which is equal to minus m omega naught square y. This is equation number 1, where m is the mass of the electron, omega naught is the natural oscillation frequency of the electron, given as omega naught is equal to K by m square root, and the K is the force constant. Obviously K is equal to omega naught square m. Value can be given as K is equal to m omega naught square m. When the electron oscillates, there will be presumably some damping force, which we assume negative times proportional to the velocity. So let's say damping force is minus m gamma times dy by dt. This is the velocity along the y-axis. The damping velocity, that is the damping force. Question 2, where gamma is the damping factor, the damping must be opposite to the velocity. Now in the presence of the electromagnetic wave of frequency omega, the velocity, the electron is subjected to a driving force given by F drive is equal to QE, the QE, now which is equation number 3, where E we take to be equal to E naught cosine omega t. So F driving force is equal to Q E naught cosine omega t. We call this equation number 4, where Q is the charge of electron, E naught is the amplitude of the oscillating electron. According to the Newton's second law of motion, putting all the above equation, that is the equation of motion when we have the oscillatory motion, that md2y by dt square is equal to all these three forces, sum of all these forces, the binding force, the damping force, and the driving force. So putting the respective terms here we get, and rearranging all these we get the equation number 5, which is md2y by dt square plus m gamma dy by dt plus k and k omega naught square. This is m, in fact this is m, let me correct that one. This is k m omega naught square y is equal to q e naught cosine omega t, equation number 5, where these terms have their already been described, the relative values as F binding, F damping, and F driving. Now the equation 5 describes a model of the electron as a damped harmonic oscillator driven at a frequency omega. We assume that the massive nuclei remain at rest. The equation 5 is easier to handle if we consider it a real part of a complex equation. So what we have, now we consider the y to be now the complex part, but a complex displacement. So we have the d2 y by dt square tilde sign we put over there. That is the real part of the complex equation. So we will discuss generally as a complex the terms, y as a complex term, and similarly displacements is a complex term. So is equal to q by m e naught e to the minus I omega t. We either use j omega t or I omega t, doesn't make any difference. We call this equation number 6. Now the electron oscillating at a driving frequency, let be the displacement with the y t is y naught e to the power minus I omega t. We call equation number 7, where y t is the instantaneous displacement and y naught is the amplitude. Now the tilde sign represents the complex function. Here we have given the all the tilde sign means it's a complex function. Since we are inside the medium, so we may have these terms. So let's now take one by one the differential dy by dt, which will give this result, which is equal to minus j y naught e to the power minus j omega t or I omega t, sorry. Okay, we take the j terms instead of I think I have used the j terms. Okay, we will see that. I think, okay, the j term I have been using. So d2 y by dt square is equal to minus y naught omega square e to the power minus j omega t. Putting in equation 6, we get y naught q by m omega naught square minus omega square minus j gamma omega e naught. So if you put all these terms in the above equation 6 and rearrange it, then we are left with the y naught. This term is obtained. Now the dipole moment associated with the motion of electron is therefore the part of a complex dipole moment as well. So p dipole moments instantaneously, we call it, is equal to q times y t, which is displacement distance between the two positions. So pt further is putting the value of q y, sorry, here, see, which is equal to y naught y the displacement, and as a whole yt is equal to e naught terms and the q square by m omega naught square minus omega square minus I gamma omega. Again, I've been using somewhere I and somewhere j. Okay, I think it's again I. We will be using the I gamma omega, not the j one. I will make that correction. Let me make this correction. Okay, so here I have made the corrections. The I will be taking e to the power minus I omega t throughout the whole this topic. We will be discussing as a iota instead of j value. So what we have, let's come to the somewhere where okay. So putting those values, we get the y naught, and the complex dipole moment is given by this relation. Now the imaginary term in the denominator indicates that the p, that is the complex dipole moment, is out of phase with E lagging behind by an angle tangent inverse of minus gamma omega by omega naught square minus omega square, which is very small when omega is far less than omega naught, and rises to pi, and it increases to pi when omega is far greater than omega naught. So this is the natural frequency, this is the driving frequency, this is the natural frequency of the oscillation of the electron, and this is the driving frequency of the signal electric field which is coming inside the medium. Now if in general differently situated electrons in given molecule exhibit different natural frequencies and damping coefficients. Now let us say that there are Fj electrons with frequency omega m and damping factor gamma j in each molecule where J is equal to 1, 2, 3 is a number. If n is the total number of molecules per unit volume, then the polarization, the complex polarization, is given as P is equal to n times the dipole moment. N is the number of the number per unit volume of these all molecules or atoms, so times the dipole moments of the each molecule or the atom. So P is equal to, putting the value of the P dipole moment over here, n q square by m, sum of all fj omega j square, this is, and minus omega naught square minus gamma j omega. So omega naught, obviously omega j's are not the natural frequencies, this is, and omega is the driving frequency, one thing you should note. So this is equation number 11. So it is P is related with the E complex. P and E both are complex. The electric susceptibility is given by the relationship P is equal to epsilon naught chi E, the electric susceptibility, times the E. P, that is the relation, which is equation number 12. In the present case, P is not proportional to E if E is to be the non-complex, so which is not linear, which is not a linear medium. However, the complex polarization is proportional to the complex E. If we take E to be complex, so this suggests that we introduce a complex susceptibility as well, chi E as a complex. So P polarization, complex polarization, is equal to epsilon naught chi E complex epsilon chi E complex in times E electric field, E field vector, complex field vector function. So the complex permittivity is also given as epsilon, complex permittivity epsilon naught times 1 plus chi E. So epsilon complex permittivity is given by epsilon naught, epsilon r, the complex relative permittivity, which is in this model takes the form. So chi E is equal to P from that previous equation 11, we get P divided by E epsilon naught. So taking to the complex, we putting the values of the respective this P value, polarization value, field vector, chi E is equal to n square n q square m epsilon naught sum of j f of j omega j minus omega square minus j gamma j omega. Since the epsilon complex epsilon is equal to epsilon naught 1 plus chi E, so putting the value of the chi E in this term, we get epsilon, the permittivity of the medium is epsilon naught times the 1 plus n q square by m epsilon naught sigma over the fj omega j minus omega square minus I gamma j times omega. Equation number 14. Now generally the imaginary term is insignificant for linear medium. However, when omega is very close to that of the resonant frequency omega j, it plays an important role. In dispersive medium, the wave equation for a given frequency is given as the del square of E is equal to epsilon mu naught del 2 by delta t square E, which is equation number 15, where E is now a complex function. Sorry, this epsilon is a complex function, which you see having this tilde sign. Omega j, function of the omega j, it gives a plane wave solution of the type we can have ext. Okay, so ext, let me propagating along x, is equal to e raised to power e naught complex amplitude e raised to power I k x minus omega t. K is again a wave vector. Now in this case it is a complex wave vector, where k wave vector is a complex and epsilon is a complex. Epsilon, the permittivity, they are related. So they are related with the k complex vector is omega epsilon complex epsilon times mu naught square root. So let k complex wave vector is is equal to k plus plus I k minus. So it's a complex wave vector. Now the E field function, which is propagating along x with the space and time both part, is given by E naught amplitude e raised to power minus k minus x e raised to power I k plus x. We have just introduced over here this k into the exponential, and then we have separated this the real part and the imaginary parts. So it is I into k plus x minus omega t, this in the bracket. Eventually k measures the attenuation of the wave, as the intensity is proportional to the E square is proportional to e raised to power minus k minus subscript x square x whole square. So let alpha a, which is called the absorption coefficient of the velocity of the wave, is equal to 2k minus 2k with the minus sign. The velocity of the wave we put here, the in that case square will make it 2k, okay, 2kx minus 2kx. So we take here as alpha, and say velocity of the wave inside the medium is given by omega over k plus the index of refraction, hence is given an n. Refractive index is equal to c by omega times the k plus, this is the k plus, that's the k plus, since n is equal to c by v, and v is equal to omega by k. For gases, the second term in the equation 14 is typically small, and we can approximate square root by using the binomial expansion 1 plus x raised to power 1 by 2, which is given 1 plus 1 by 2x. Since the k is equal to omega by c epsilon or epsilon naught, so what that we have the term from the above, because we have got all these terms, n is equal to c by v, and v is c by omega k plus, so we can put over here, and the k is also we can get the k plus from here, k as a whole, omega by c epsilon over epsilon naught. So we have epsilon is the permittivity, complex permittivity is given by this term. Putting all this in equation number 22, what we get, k, but we replace here in this case the value of the epsilon, this one here. So k is given omega by c, and inside you simplify the things, we get the finally, and making the binomial expansion of the whole term, this is the final result. What we get, k is equal to omega by c 1 plus m q square by 2, this is the binomial 1 by 2 comes down here, and rest we ignore the higher order of this term, and we are left with this result as equation number 23. Since n is equal to c by omega k plus, and k is equal to k plus plus I k minus, which is equation number 25. So first we rationalize the equation 23, this one, because the I is the complex part is in the denominator, we have to take it to the numerator. So multiplying and dividing by the omega j minus omega, what we get here, square omega j square, this is minus this whole term, rationalizing the here, what we get, omega j square minus omega square, the terms we will here, the rationalization I have just reduced the, just go through that, multiplying and dividing. So we will get two terms over here, one is the real term, the other one is the imaginary term. So multiplying and dividing this this part, again this, if this is minus, when we multiply it with the omega j square minus omega square plus I gamma j omega. So we multiply and divide this term to rationalize it. So after rationalizing, we get, then we multiply the old terms, and get the real and imaginary part separate. So in this case, omega by c plus omega n q square by 2 m epsilon naught c sum of fj omega j square minus omega square, and this whole term omega j square minus omega square whole square plus omega j the gamma j times omega whole square. And similarly the other term with the I, but in the numerator we have got this term, which is the obviously the second part of that, which is the fj omega, this is omega gamma j, omega gamma j. So the comparing the equation 25 and 26 now, because this now both are the complex now, the real and imaginary part we compare, then we get the k plus is equal to omega by c, and this whole term here you see in this case this whole term is k plus and this is the k minus, this whole term is k minus. So k plus is equal to omega by c into 1 plus n q square by 2 m epsilon naught sum of j fj omega j square minus omega square divided by omega j square minus omega square whole square plus gamma j square omega square, while the alpha a absorption coefficient is equal to 2 times k minus. So k plus, here we take this wave vector, and the alpha a, the n q square omega square over m epsilon naught sum of f of j divided by omega j square minus omega square whole square minus gamma j square omega square. So this is these are the finally obtained terms. We can see that the wave vector, the complex wave vector with the k plus and k minus terms, which are responsible for the dispersion. And you can see now there are various, the graph between the n and the alpha, and these coefficients are drawn. You can study now further and see that the dispersion takes place. The responsible parameters are inside, obviously the reflectors, which they play important role. We came all the through, which is the electromagnetic permittivities, which is the epsilon was the main factor. We saw it was affecting the incoming electric field, so that was causing the dispersion, that is the causing the refractive index change in the respective refractive index. So with this we reach to the end of this topic for the dispersion. It's a bit lengthy, but mathematically we have to go through and have to find the respective factors. Okay, thank you for the moment. See you next time.